Mechanisms of increased atherosclerosis in renal failure. The next section will further illustrate the importance of the enhanced systemic vascular inflammatory response. In the patient with renal dysfunction, reduced amounts of nitric oxide are produced by the endothelial cells. Yet the dysfunctional endothelial cells now release increased amounts of the vasoactive and pro-inflammatory agents angiotensin and endothelin. A suggested mechanism of the reduced nitric oxide in patients with renal dysfunction implicates an increase of caveolin. Caveolin decreases the bioavailability of enos and as a result results in decreased production of nitric oxide. Furthermore, the absence of both absolute and relative BH4 tetrahydrobiopterin now prevents nitric oxide synthase to be coupled in its active dimeric form, and consequently facilitates the production of reactive oxygen species such as superoxide and hydrogen peroxide. The activated endothelial cells in the patient with renal dysfunction are primed to develop an intense inflammatory response. Receptors are expressed on the cell membrane that attract pro-inflammatory stimuli, as well as attracting cells that further promote the inflammatory response. Increased amounts of oxidized LDL bind to the receptor LOX1, which is upregulated in patients with renal disease. Stimulation of this receptor triggers intracellular oxidative stress, increasing reactive oxygen species production. Furthermore, upregulation of LOX1 in patients with renal disease increases the nuclear transcription factor NF-kappa B. NF-kappa B is responsible for the upregulation of a variety of inflammatory markers such as ICAM, VCAM, MCP1, which attract and bind monocytes to the dysfunctional endothelium. Once bound, the leukocytes transmigrate through the endothelium. Once within the arterial wall, the monocytes interact with upregulated T cells, which facilitate the conversion of monocytes to become macrophages. These macrophages engulf LDL cholesterol and foam cells develop. These foam cells accumulate in the subendothelial space. The next stage in atherogenesis is the process of neointimal formation and the migration of vascular smooth muscle cells into the plaque. The smooth muscle cells become part of the neointima, forming the fibrous cap overlying the foam cell core. With the development of the neointima and increased foam cell accumulation, the plaque development progresses. The vascular smooth muscle cells lining the fibrous cap are part of a fibrous matrix, which also contains an inflammatory cell infiltrate. The inflammatory cells are responsible for synthesizing enzymes such as metalloproteinases, which can degrade the fibrous matrix. One important component of the inflammatory response in patients with renal disease is the increased levels of circulating C-reactive protein. In patients with renal disease, CRP is produced by both the kidneys and the liver and interacts with the dysfunctional endothelium. C-reactive protein is not only a surrogate biomarker of future cardiovascular events and death in patients with renal disease, but also plays an important role in the promotion of the inflammatory response. C-reactive protein directly incites endothelial dysfunction as well as intensifying the inflammatory response. CRP decreases nitric oxide production. It directly increases reactive oxygen species synthesis and increases the production of endothelin-1, whilst also upregulating the angiotensin cascade in vascular and smooth muscle. CRP also directly facilitates the upregulation of the nuclear factor NF-kappa B, consequently further promoting the inflammatory response. As a result, high levels of CRP in patients with renal disease may be linked to atherogenesis through their effects on endothelial dysfunction and vascular homeostasis. Recent evidence is indicating that patients with renal disease have a dysregulated interaction between platelets and the soluble CD40 ligand. The receptor for CD40 ligand is also present not only on the endothelial cell and platelets, but also within the plaque and on vascular smooth muscle cells. Increased levels of soluble CD40 ligand in patients with renal disease bind to the CD40 receptors on the surface of macrophages and smooth muscle cells in the fibrous cap and media, triggering a massive intracellular inflammatory response, as well as increasing both tissue factor and the metalloproteinases responsible for degradation of the fibrous cap. In addition, cytokines such as TNF-alpha, IL-1, and IL-6 are expressed, further enhancing the inflammatory milieu. Metalloproteinases secreted by both the smooth muscle cells and inflammatory cells within the fibrous cap degrade the collagen matrix, weaken the fibrous cap, and lead to conditions that promote fibrous plaque rupture and the chain of events that result in thrombotic occlusion of the artery and an acute coronary syndrome. Phosphate accumulation in patients with renal dysfunction may play an important role in the dystrophic calcification and degeneration of the arteries. The metabolic derangement resulting from phosphate accumulation stimulates the parathyroid gland to secrete parathyroid hormone. The resulting retention of calcium and increased circulating levels of calcium are responsible for the extensive dystrophic calcification observed in the arteries and other sites in the patient with renal failure. Not only does calcification impair the elastic properties of the arteries, it may also play a role in plaque disruption.